let's suppose I have a function, a very simple function, x squared. And let's suppose we are asked to find the area under x squared between 0 and 2. Okay. Why? I'll explain later. So for now we are just thinking about the technicality. How we are able to determine, how do we determine the area under the graph. So this is 1 and this is 2. 1, 2, 3, 4. I graph the function between 0 and 2 only. This is at 0 is 0, at 1 is 1, at 2 is 4. Here is the graph. And the area in question is this. So this is what we're asked to find. At this point, we cannot really find the exact area. We will very soon. We will be able to next week. By next week, a week from today, we will be able to find the exact area. Right now, we are happy with approximations. So approximate the area using 4 subintervals. And left most point, right most point, midpoint. What's all this? Okay, so I'm going to graph that 3 times. So for now, I think I'm only 12, yeah. So for now, I'm going to enlarge it. So this is the area in question. This is 0, this is 1, this is 2. The function is still x squared. I want 4 subintervals, and I want the leftmost point. Okay, if I want delta x is the width of each subinterval. So how much is delta x with n equals 4 subintervals? Well, delta x is b minus a divided by n. b minus a, the interval, is a comma b. b minus a, 2 minus 0 divided by 4. So 2 over 4 is 1/2. So this is the first subinterval, where this is 1/2. And this is the second subinterval, between 1/2 and 1. This is the third subinterval between 1/2, 1 plus 1/2, which is 3/2. And this is the fourth subinterval between 3/2 and 2. Now, what does the leftmost point mean? It means that I will split this area into rectangles. So the rectangle, the first rectangle will have the height at the leftmost point. There is no height. The width is 0.5, but there is no height, it's 0. The next subinterval will have the height at the leftmost point, and it will have this area. The next subinterval will have this height, and it will have this area. And the last subinterval will have this height, and it will have this area. How do I write all this? Area with the left 4 equals base times height, base times height, base times. So base is always delta x. I'm going to put it outside. F of 0 plus f of 1/2 plus f of 1 plus f of 3 halves. We're going to get the number in a minute, but I want to ask you, will this be an underestimate or an overestimate of the exact area?
Would be an underestimate.
Under?
Of course, look at all these blanks, right? So this will be an underestimation. Underestimate. Very good. So, I have 0.5 outside. This is 0. This is 0.5 squared. Plus, this is 1. Plus, this is 1.5 squared. And I'm checking my numbers. That's a 0 and that's 0.5 squared. And yep. So I got 1.75. Our second option. Still the same graph. Still the same limits here. The 0, the 1/2, the 1, and 3 halves, and 2. But this time we're going to use the rightmost point. Okay. So base times height. So this is the area. Base times height. The rightmost point. Base times height. This rectangle now. Up. And base times height. So the area right for will be, base stays outside because all of them will have this time. Now I have f of 1/2 plus f of 1 plus f of 3.5 or 3 halves. I meant to write 1.5 or 3 halves plus f of 2. Will this be an overestimation or an underestimation?
Over.
Yes. Look at all these. They're outside. So overestimate. Perfect. Again, I'm going to plug it in and see what I get. So 0.5 in front, and I have 0.5 squared plus 1 plus 1.5 squared plus 4. Close the parenthesis, enter. So this is 3.75. So I know that this is too low and this is too high. Okay, here's the last one. Still 0, still 1/2, still 1, and 3 halves, and 2. And here is our next step. Midpoint. The height is at the midpoint. Here's the area. The height of the rectangle is at the midpoint. The height at the midpoint. And the height at the midpoint. Which of these three you think will be the closest to the actual exact area?
Midpoint.
Yes. Best approximation from all three. Okay. So this is A with M4 equals. Still 1/2 outside. But now I have to figure out these points. So this is 0.25, this is 0.75, this is 1.25, and this is 1.75. So f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. Let's see what that gives. 0.5 in parentheses 0.25 squared plus 0.75 squared plus 1.25 squared and plus 1.75 squared and close. Let me check. Yes, 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 yes. Okay. So this is 2.625. We expect this to be the closest to the exact area. Okay. Notice what we just did. What did we do? In all these situations, let's go back to the first one. This is delta x. But we multiplied it by f of x1. And then delta x times f of x2. By x1 I say 0, and then 1/2, that's x2, and that's x3, that's x4. And so on and so forth. So what did I really do? I created a sum of base times height. The base did not change, but the height always changes. The height here is 0, the height here is f of 1/2, the height here is f of 1, the height here is f of 3/2. So from subinterval to subinterval, the base does not change, but the height of the rectangle always changes. So this depends on the index, from the very first subinterval to the very last one. In this case, we had from I equals 1 through 4. 1, 2, 3, 4. Delta x times f of x1 plus delta x times f of x2 plus delta x times f of x3 plus delta x times f of x4. So this is called Riemann sum by the mathematician who thought about it. It's called the Riemann sum. Stay with me. So, I'm going to ask you this question. We used n equals 4 subintervals. And we were happy with the midterm. Not the midterm, no. With the midpoint. I'm asking you now, what if I use, let's say, 8 subintervals? Instead of 4, I will have 8 subintervals. Will these approximations, if you want, will the midpoint be better, a better approximation, closer to the exact, yes or no?
Definitely yes.
Perfect, of course. What if I go to 16? Will that be better?
Much better.
Much better. What if I go to 128? Will that be better? Where should n go to for you to be fully satisfied? That the
Infinite amount of rectangles?
Of subintervals or rectangles, the same thing. Awesome. But what does this mean? We've seen this before in the entire semester, almost from day one. What does this really say to us? What are we looking for when we say n approaches infinity?
Limit?
Exactly. So the limit as n approaches infinity from this Riemann sum, from I equals 1 through n, from delta x, f of xi. This has I because it changes. When I is 1, this is a value. When I is 2, this will be another value, and so on and so forth. This will be the exact area. Exact. No approximation whatsoever. So we would write that the exact area is the limit of the Riemann sum. The exact area is the limit of the Riemann sum. Any questions? I promise to stop after we calculate one limit.